So today I want to tell you about magnetic fields, and both about observing them, summarizing some of the real observations, and then about observing them in the computer. So I'll give you a historical introduction, and then we'll talk about some of the recent observations, and then something of particular interest and relevance for this workshop is how you can try to observe them on the computer. Now I'll talk about a particular problem which Eve alluded to yesterday, which is the so-called protostellar accretion disk crisis. And then I'll wind up by talking about what we find as apparent violations of magnetic flux freezing. So the interesting thing is that many decades ago, in fact in the first paper here, Mistel and Spitzer, more than half a century ago, theorists started worrying about the effects of magnetic fields in star formation. And when you think about it, it is truly amazing that they were already writing papers about this, because at that time there were no direct measurements of the magnetic field. There were indirect observational arguments, namely you saw polarization of starlight, and so people scratched their heads and said, well, maybe the polarization of starlight is due to dust grains being aligned in a magnetic field. So that's kind of an indirect argument for a magnetic field. And then Fermi had a great idea for how to make accelerate cosmic rays that involved colliding magnetic clouds, sort of second order Fermi acceleration. So that was evidence for magnetic field. So, basically I would say those are pretty tenuous arguments, and neither one of them really gave you any feeling about the magnitude of the field. But despite that, theorists were able to go ahead and study the effects of magnetic fields and actually do it in fairly realistic values for the field. The key idea that they developed was that the magnetic energy, since the magnetic energy scales with the gravitational energy, there is a magnetic critical mass. So if you look at the equation I have up there, you have the gravitational energy, that's gm squared over r, and divide by the magnetic energy, which is proportional to the square of the magnetic field times the volume. And then if you bring that r that's in the denominator of the gravitational energy and move it down to the denominator, you get b squared r to the fourth. That's proportional to the square of the flux. So what you have then is that the ratio of the gravitational energy to the magnetic energy is proportional to the square of the mass divided by the square of the flux. And if the two things are equal, when the mass is equal to a critical value, and that critical value is the magnetic flux divided by 2 pi times the square root of g. Now the 2 pi I put in there corresponds to the condition for having you have a uniform magnetic field and threading a sheet of gas, then the 2 pi is the condition that you need for to get instability. But you can show that it's comparable if you go ahead and look at more realistic spherical cases as well. So you may have read when you're studying star formation that there are two classical problems that emerged in these very early papers. And the first paper is the magnetic flux problem. In fact, there are two magnetic flux problems. The first one is, how is it possible for the amount of gas to build up so that it can overcome the effects of the magnetic field? And in other words, get the mass to be bigger than this magnetic critical mass, m sub phi. There's a second problem which quantitatively is far larger, and that is, once you become magnetically supercritical, you still have a magnetic flux which is between 100,000 and 100 million times as large as the magnetic flux that's observed in main sequence stars. So how do you get rid of that huge amount of flux? That's a separate problem that is resolved during the formation of the stars at very high densities. And I'm not going to go into that today. I should say I'm not sure that it's actually been adequately resolved even today. The second classical problem is the angular momentum problem. You can estimate the amount of angular momentum that you get in interstellar gas by just looking at the amount of angular momentum that you have because of the rotation of the galaxy. And then you look at the amount of angular momentum in the solar system, and you can see that there's a huge discrepancy by a couple of orders of magnitude. So where does that go? So interesting enough, Spitzer long ago figured out that the first problem could solve the second problem, that is magnetic torques could be very effective at removing angular momentum. In fact, in this earlier paper with Leon Mestel, they had speculated that the removal of the angular momentum could be so efficient that you would not form a disk around the star. And that leads to what is called the protostellar accretion disk crisis. But I want to emphasize that this was now a half a century before protostellar accretion disks were even, or not a half a century, but many decades before protostellar accretion disks were even discovered. So we'll see that the loss of magnetic flux that is solving the first problem also then solves this protostellar accretion disk problem. So let me go in a little more detail now on this magnetic flux problem. So I've said that we have this magnetic critical mass, which is the magnetic flux phi, divided by this constant 2 pi times the square root of Newton's constant. So you can then take the ratio of the mass to this magnetic critical mass, and you can see that that's just proportional to the mass to flux. So oftentimes people refer to the mass to flux ratio, and then you can measure it in this critical units, and then that's what this quantity mu sub phi is. So people then refer to some systems as being magnetically supercritical. That means that the gravitational energy is greater than the magnetic energy. Mu phi is bigger than 1. You have a large mass to flux, and that means that in principle the cloud can collapse. On the other hand, if it's subcritical, where the gravitational energy is less than magnetic energy, mu phi is less than 1, and the cloud can't collapse. And I want to emphasize, if you have an isolated cloud and you have ideal MHD, so the flux is frozen into the cloud, then you can do anything you want to that cloud. You can compress it, have a strong shock wave, much stronger than the ones that Eve was talking about yesterday. Have a shock wave come in, at 1,000 kilometers per second, compress the cloud to a factor of 1,000,000 or 100 million times greater than its initial density, and it will not gravitationally collapse. Nothing you can do, so long as you have ideal MHD, can cause the cloud to collapse if it's magnetically subcritical. So in ideal MHD, the mass to flux ratio can in fact only decrease, well, it can only increase, I should say, due to mass flow along the field lines. And so mass transport across the field is impossible. So if you imagine the field then is, say, vertical in this room, going from the floor to the ceiling, then I can go ahead and I can have mass flow along the field lines and form a cloud. And if I have more and more mass come in, the mass to flux ratio of that cloud can increase. However, as long as you have ideal MHD, you have no flow of mass across the field lines. Okay, so Mestel and Spitzer pointed out that the diffuse interstellar medium is magnetically subcritical. So they concluded that stars could not form. Remember, back at that time, molecular clouds had not been discovered. So they had an idea what the mean density of the interstellar medium was, and it was magnetically subcritical. So let's look at that argument with modern numbers. So let capital N be the column density. It's just the density times the size along the field. And then if we write down the mass to flux ratio, taking out this constant, the 2 pi root g, then you get the mass, which is the column density times the mass per particle, then times the area. And you divide that by the flux. So that's the magnetic field times the area. So you see the area cancels out, and you get a relation which is just between the density, the length along the field, and the magnetic field. So you can then solve for what this length is, and you get a very amazing result. You find that I'm trying to find that, how big a region in the interstellar medium I need to be magnetically supercritical, and I get a number that starts off with 500 parsecs. And now the 500 parsecs I divide by the mean density. Well, the mean density in the interstellar medium is 1 particle per cubic centimeter, so that doesn't change things. I've normalized the magnetic field to the value that is measured in the diffuse interstellar medium. So this region, this is a huge region in the stellar medium, far, far larger than the size of a region that you need to form a 1 solar mass star. So they concluded that magnetic fields exceed gravity on stellar mass scales in the diffuse interstellar medium. And the length scale required to change this is too large to be effective in forming stars. We don't want to have gas have to flow 500 parsecs to form a star like the sun. Now, interesting enough, this length scale is in fact the length scale that is involved in the formation of giant molecular clouds. So but these objects were not discovered until 20 years after this seminal theoretical work. Okay, so what Mistel and Spitzer concluded is you needed something to, I said before, in ideal MHD I can have the gas flow along the field lines, but it's impossible to flow across the field lines. Ambipolar diffusion is just such a process. It is not an ideal MHD. It does allow gas to flow along the field lines. And the basic physical principle is that it is only the charged particles which feel the magnetic field. The neutrals do not. So the neutrals can perfectly well cross field lines. They get, however, slowed down in this process by the drag that they feel with the ions. So they, Mistel and Spitzer worked this out. And in fact, this then led to what was the standard paradigm for low mass star formation. And I've taken this famous cartoon out of the review article by Hsu, Adams, and Lozano in 1987. And the basic picture then is that, at least for low mass stars, you had the gas that would form a star would have a magnetic flux which was too large, and therefore you would have to wait until the gas could contract along the field lines in order to become gravitationally unstable and then form the star. And Telemachus Mousavias and his students have been done most of the work on this theory. Okay, so that finishes the theoretical introduction. Let's talk about some of the observations. So there are two types of observations. Let me start, and we're going to focus on the Zeeman observations. And what the Zeeman observations do is that Zeeman discovered that you get a splitting of lines if you have an atom or molecule in a magnetic field if there's an unpaired electron. And there are a few species. Fortunately, atomic hydrogen is one of them. It just has one electron. And there are a couple others we'll talk about where you can have this. And then you go ahead and you measure this splitting, and the result that the radio astronomer gets is they find the product of the column density and the magnetic field along the line of sight, which I abbreviate as just LOS. Then we want to define what is the total magnetic field. So first, remember, I'm getting the integral of the magnetic field along the line of sight. So if the field, say, is going this way, right, say out there, there's the observer, then you get the actual magnetic field. Now, what if that's in part of the cloud, but in another part of the cloud that's in your beam, there's some magnetic field going that way? Well, these fields then cancel out. So this is actually, when you do this integral of the magnetic field, you're taking into account the sign of the field. It's not just its magnitude. But of course, typically, the field is not going to be so conveniently oriented to be aimed right at the observer. The field is going to be at some random angle. And so because half the sky is at an inclination of greater than 60 degrees, the median angle is at 60 degrees. And so if you take the sine of that, you wind up getting that the component along the field is half of the total. So you find that, in other words, the total magnetic field, the median value will be twice the median value of the line of sight field. So the atomic interstellar medium is indeed magnetically subcritical, just as Mistel and Spitzer inferred. So Hylas and Troland actually went ahead, and now they're able to measure that directly using the Zeeman effect in atomic hydrogen. They found a mass-to-flux ratio less than 1/6, so it's very magnetically subcritical. However, both theory and observations have shown that GMCs are magnetically supercritical. I developed an argument some years ago which suggested that the mass-to-flux ratio in GMCs would be about 2 because gravity had to overcome both the magnetic field and the turbulent motions in the molecular clouds. Observation, of course, is better. If you look at the cores inside molecular clouds, then Dick Crutcher summarized the data somewhat over a decade ago and found that typically the mass-to-flux ratio was greater than 1, and the Alfvén Mach number was of order 1. More recently, he collaborated with Tom Troland, and they had OH observations with the Arecibo telescope and found that, again, the cores were magnetically supercritical with a median value, depending upon exactly how you correct for inclination, between 1.7 and 2.6, and the median Alfvén Mach number was about 1.5. Now, the most recent thorough study of the magnetic fields in the interstellar medium was in a paper by Crutcher et al. In 2010. He updated a little bit in his annual reviews article a couple of years later, but I'm using here the data in the 2010 paper. And he summarized all the data that was available at that time. And this had three different sources. You had the atomic hydrogen, which I've already mentioned. You have the OH molecule, which is mainly sensitive to gas between about 1,000 and 20,000 per cubic centimeter. And then the CN molecule, which is between a couple 10 to the 5 and a few 10 to the 6th. And so this is the graph then shows the field in these different density ranges. So this is primarily the H1 data, this is the OH data, and this here is the CN data. So, and I also then want you to notice that basically, you see that there are these very long lines here. That's because they found actually that only 27 of the molecular cores that were detected. So the molecular cores are the ones that are the OH ones and the CN ones. So a little bit less than half of them actually had a detected magnetic field. Over half, they just had upper limits. The more sophisticated thing that Crutcher and his collaborators did in this paper here was instead of throwing out the upper limits, they actually included them. Okay, so by using a Bayesian analysis. And the results that they found is if you focus on the just the cases up here, so the OH points and the CN points, then they found that the total magnetic field, which they inferred, remember they cannot measure that. So they measure the line of sight field, and then they do an analysis in which they assume that the field is randomly oriented, and then they infer a total value of the magnetic field. And they found that that scales with the density as about the 0.65 power, basically about the 2/3 power. The median value of the mass to flux ratio is consistent with previous results. And they also inferred that the distribution of the field strengths they saw was consistent with the uniform distribution, which goes from some value F times B max up to B max. Now again, I want to emphasize they cannot measure this, right? They measure the line of sight field, and I'll talk about that a little bit more now. They then have a model, and they do a statistical analysis to try to infer what the total field is. And they did not do an inverse problem. That is, they didn't solve for it. They just tried like a delta function model, which theorists like to use, because they just assume that it's all the same. And they showed that this square thing here is orders of magnitude better than a delta function. Now, he verbally has told me they also showed it was better than a log normal, but that the details were not in the paper. And they found that F was very small. It's only about 0.03. And so what that says is that actually a significant fraction of the volume in the interstellar medium has a very low magnetic field. So the Zeeman observation I've just described referred to clumps on a scale less than a few parsecs. What about the structure of the field on much larger scales? So here I want to refer to some work by Huabai Li and his collaborators. And they did an amazing thing. They looked at the structure of the field on 200 parsec scales compared with that on the less than 1 parsec scale in molecular clouds. So this, you might think, really has nothing to do with each other. I'm now looking outside the molecular clouds. I'm looking at, atomic gas where I can see stars in the distant and measure the polarization of the starlight. And then I'm going to go inside a molecular cloud and look at use radio telescopes, sub-millimeter array and so forth, and get the magnetic field on very small scales. And so here's what they found. They plotted the magnetic field, the angle of the magnetic field that in the cores inside the clouds on very small scales, less than a parsec, against the angle of the field in the surrounding atomic gas on scales of a couple of hundred parsecs. And they just plotted this up. And the dark part is within 30 degrees and the yellow part is within 45 degrees. And the result that they got was that 90% of the cores have a field aligned to within 45 degrees, whereas randomly you'd expect only half. So what that means is that there is a strong correlation between the large and the small scales. You cannot have very weak magnetic fields. So the cores may be magnetically supercritical, but they can't be too supercritical. Okay, so the conclusions on the observations are that the Zeeman observations that measure this integral of the density times the field along the line of sight show that the molecular gas is magnetically supercritical. In other words, gravity dominates in molecular gas. And that's good because that's where stars form. There are no OH cores and only one CN core, which are magnetically subcritical. Oops, if you, pardon me. So hopefully that will shut up. Okay. So there are no. Okay. If you just try to measure the magnetic critical mass using the line of sight field, then there is really no OH cores and only one CN core, which are subcritical. Then, as I said, Crutcher and collaborators inferred that the total magnetic field varies as the density to the 0.65 power in molecular gas. They also inferred that this total magnetic field divided by the density 0.65 is uniformly distributed from a very small value to some maximum value. And then somewhat a counter to this, Wabai Li and company compared the structure on very small scales to that at very large scales and showed that there was a good correlation. So the magnetic field is, in fact, it cannot be too weak. Okay. So we can now try to observe, see if we can understand this by using simulations. And the observations, as I said, they measure, the Zeeman observations measure the integral of the density times the line of sight field. You also can get polarization observations, and the fluctuations in the orientation of the polarization give you an estimate of the magnetic field strength in the plane of the sky. So in other words, if I have a very strong magnetic field, then say all the field lines are perfectly straight, then when you measure the polarization, the dust grains are going to be spinning like that. They will absorb the radiation with the polarization that has the plane parallel to the floor and pass the radiation that is polarized along the magnetic field. On the other hand, if I start wiggling the field lines around, then I'm going to start getting a dispersion in the directions of the polarization. And I can then relate the magnitude of that dispersion to the Alfvén Mach number of the gas. So if I have a very low Alfvén Mach number, that is very low velocities, then I'm going to be very close to this uniform field case. I'm going to not have fluctuations. If I have a very high Alfvén Mach number, that means the magnetic field is weak, and I'm going to get random orientations. So that was worked out by Chandrasekhar and Fermi more than half a century ago. So the advantage, of course, of doing the numerical simulations is that we get the full 3D field. So rather than trying to infer it from these two different observations, I should say generally these observations are not available for the same sources. So you have some sources where they've done Chandrasekhar and Fermi and some where they've done the Zeeman. Okay, so what we did is that we used the Orion 2 ideal MHD code with adaptive mesh refinement, and you've heard a lot about AMR codes in the earlier weeks. So the physics that we included then was just ideal MHD and self-gravity. We had periodic boundary conditions. We drive the turbulence at large scales, wave numbers between 1 and 2 on the box length, and we do that throughout the simulation. We turn on the gravity after one freefall time. So in other words, what we want to do is to build up a self-consistent turbulent density structure before we allow gravity to operate. And this is actually a very profound difference in the community. There are half the people like us who go ahead and set up the density structure and then turn on gravity, and half who don't. and it has a huge impact on what you find. So we tend to find clumps because we've already essentially created them. And I should say, I want to emphasize, of course, the interstellar medium is observed to be clumpy, both in the atomic and molecular gas. Whereas if you start off with a very uniform gas, even if you try to go ahead and stick in some turbulent velocities, then you tend to get a much smoother flow, and you tend to get different results when you work out what's happening for star formation. So we had then a 512 cube base grid and with a couple of levels of refinement. So that's altogether equivalent to 2048 cubed calculation. Our dimensionless parameters, we had a sonic Mach number of 10, an alpine Mach number of 1. The gravitational energy was about equal to the turbulent energy, and it was magnetically supercritical. The mass to flux in critical units was 1.62. So one of the key things about doing simulations, which you may have heard about, I don't know, is that when you're doing a simulation with isothermal MHD, they are completely scale-free. You can set the mass, the size scale, and the time scales arbitrarily. There is no physics. So you do one simulation like this, and you've done them all. Now, when you start adding in more physics, then you start pinning things down. So, for example, we included self-gravity, so that introduces Newton's gravitational constant. Then you get we have a dimensionless parameter, the virial parameter, which measures the ratio of the kinetic energy to the gravitational energy, and we set that in order 1. So that sets one scale. Now we have only 2 free parameters. Molecular clouds generally have temperatures of order 10 Kelvin. So setting a Boltzmann's constant times the temperature corresponding to a temperature of 10 K, that then sets another parameter. And finally, the final dimensional relation is to use the line width size relation. So it has been observed for a long time. This was first noted by Larson in 1981, that the larger the scale you look at in the interstellar medium, the higher the velocity dispersion. And this is a characteristic of turbulence. People studying earthbound incompressible turbulence had shown that the velocity perturbation scale like the 1/3 power of the size in incompressible turbulence. In supersonic turbulence, it's expected that instead of the 1/3 power, it's about the 1/2 power. And indeed, this is about what's observed. And putting the coefficient in, the RMS velocity is a little less than 1 kilometer per second in a region which has a scale of 1 parsec. So if I now I have to set mass, length, and time. I now have the 3 parameters that I can do. That gives me my mass. It's a little over 3,000 solar masses. The size of the box is about 4.5 parsecs. The density is almost 1,000. I'm going to get my magnetic field from one of the dimensionless parameters I had, which was the mass to flux ratio, so that determines that to be about 30 microgauss. And the finest resolution, at the finest level of refinement, is 500 AU in this 5 parsec box. So here is a volume rendering of the situation a half a free fall time after gravity is turned on. And you can see that it's very turbulent. There is sort of an overall large filamentary structure here that you can see, and there are some other filamentary structures going here, and then you can see some other filament. So just as Eve mentioned yesterday, you do get a lot of filamentary structures when you are doing these supersonic simulations. And because of the compression associated with the supersonic motions, although the mean density, as I said, is about 1,000, half of the mass of the gas is at a density more than 5,000, so it's substantially compressed. So we then took out a sample of molecular cloud cores out of this. So remember, the Zeeman observations referred to cloud cores that astronomers had observed. We now want to observe our simulation. And so we first of all, we've analyzed it several different times. I'm going to show you the results a little bit more than half a free fall time, which corresponds to 800,000 years after we turned on gravity. We used a routine called clump find, which was developed by John Williams many years ago to identify the clumps. we merged all the cores that were separated by less than 0.06 parsecs. That's a somewhat arbitrary thing, but in the data that we were analyzing, which had a wide variety of resolutions depending on how far away the clouds were, the finest resolution was 0.03 parsecs. So there's no case where you can have cores separated by less than 0.06 parsecs in the data. So we just went ahead and merged them all in our simulation also. We then chose the 100 most massive cores. The minimum mass was a little over solar mass. And to compare with observation, we then just looked at a central beam. So you have some complicated shaped core, and what the astronomers do is instead of going out and measuring, making a map, they want to get the Zeeman observations because they're very time consuming. They just look right down at the very central brightest region where they're going to get the strongest signal. And the typical value for the size of one of these cores is about 30% of the radius or the size of the cloud. So that's what we did. So these regions are well resolved in our simulation. They all have more than 10,000 cells. In fact, the median is almost 50,000 cells inside the cores that we're looking at. So here's a picture of one of these cores at much higher resolution. And I want to emphasize that this whole size here now is just about 0.02 parsecs. The mass is about 11 solar masses. There are a few field lines here, and you can see they're somewhat tangled, and they're twisted. And the total, the peak magnetic field here is almost a milligauss. Remember, we started out with a field only about 30 microgauss. So we have a substantial increase. However, in the data that we're going to analyze, we have smeared out everything to 0.03 parsecs. And then we just look down at the central 30% of that. So we don't see in the data I'm going to present to you, we're not analyzing a map of this. We're just really smoothed it out. Okay, so the first result we find is that we get a scaling of the magnetic field that agrees with observation. So as I pointed out, Crutcher and company found that the total field varies as n to the alpha with alpha of 0.65. What we find in this 100 core sample is at this fiducial time that we're picking to analyze the data, we get alpha 0.61 plus or minus 0.1, so that's consistent. If we average the different times that we looked at the data, then in fact we get 0.68 plus or minus 0.05, so that's even somewhat more accurate and again is consistent with observation. So that I think is a very striking confirmation of the fact that at least we seem to be on the right track in simulating the data. Now for the 68 cores that they had, they found the median, the line of sight field compared to the density of the 0.65 was about 0.028. And what we find is, for that same number, we find a 0.016. The total field, which they can infer, but we can actually measure, has this ratio of 0.035. So, as I mentioned at the beginning, you expect the total field to be about twice the line of sight field, and that's true, so that is consistent. And the simulated field here is about 60% of the observed value. And well, I'll just mention this now also. This is amazing, because remember, we had some arbitrary choices to make at the beginning. I decided to use the line with size relation. I didn't emphasize the fact that that line with size relation has a variation of a factor of 3. So that I said it's about 1 kilometer per second on a scale of a parsec, but it can also be 3 kilometers per second or a third of a kilometer per second. So I just, picked a number. The other thing is we did one simulation. The data that I've showed you are drawn from all over the sky. They have wide range of initial conditions. So it is truly amazing that we get dimensionally even within better than a factor of 2 of the observed value here. So what about the distribution of the line of sight fields? That also agrees with the observation. So here we have the number of objects versus the ratio of B, the line of sight B normalized to n to the alpha, and then divided by the median value. And the gray part are our simulation, and the whites are the observations. And you can see they agree pretty well. And if you do a Kolmogorov-Smirnov test, you get that it's in fact is consistent with being similar to the data. The p-value is 0.5. And again, I emphasize that this is amazing because we had one simulation, and the observers have a wide range of molecular clouds. So what about the simulated distribution of B total? So this box here is what Crutcher and company would say. They had this goes down to 3% of the maximum value here. And this is what we find. We find that it doesn't look very uniform at all. And the value of F that we have, the weakest field, is only 10% of the max, not 3%. And if we go ahead and try to do a log normal fit, we do very well. We in fact get the p-value here is almost 1, and the width of the log normal is not very wide. So rather than having things uniformly spread from 0.03 to 1, we have a log normal which has a dispersion of only a factor less than 1.7. The field line tangling prevents very small values of the RMS field, particularly in the more massive and or denser cores. So here we've correlated the ratio of the total field to the RMS field. So remember, the total field now depends upon the sign. So if I have part of the field going this way and part going that way, that cancels out to 0. Whereas the RMS field, of course, you add up do the root mean square, so it doesn't cancel. And this shows that B total over B RMS, as you go to higher mass or higher density, then the RMS field gets larger and larger. So in the 100 core sample, the smallest value of B total divided by n to the 0.65 that we got is about half the median value. And that number of 0.47 is about twice as large as the one that the Crutcher model. The smallest RMS is 1.4 times this median line of sight. So this now says the smallest RMS field is about 3 times larger than the smallest total field. So we then conclude that the very small fields that are inferred from the Zeeman observations are due to tangling along the line of sight. So what about ambipolar diffusion? So it is the dominant non-ideal MHD effect when your density is less than about 10 to the 10. You can define a ambipolar diffusion Reynolds number, which is kind of like a hydrodynamic Reynolds number, in which you divide LV by the magnetic diffusivity, and if you put that in, this gamma AD is the ambipolar diffusion coefficient. So that's basically the product of the cross section and the relative velocity from ion neutral collisions, and these are the densities of those. The observed values for cores with measured values of the magnetic field is about 17, and if you work out what you expect theoretically, you can calculate that you expect to get about 20 times the square of the alpha and Mach number divided by the square root of the virial parameter. Both these numbers, this number is observed to be 1, about 1, and this number is also border unity. So the observed values that are consistent with the theoretical expectation. So they expect that the ambipolar diffusion is going to be dominant on length scales which are smaller than the observed length scale L by this ambipolar diffusion Reynolds number. So in other words, once you get down to 5% of the length scale or so, then you're going to have ambipolar diffusion be dominant. So the conclusions from the simulation of the magnetized molecular cloud is that we have this excellent agreement between the dependence of the total field with density and this power law exponent. We got 0.68. If you average over time, the observed value is 0.65. Both are consistent with 2/3. They get very good agreement with the observed distribution of the line of sight field divided by n 0.65. So I want to emphasize when I use the line of sight field, that's now a completely observed quantity. That's not modeled, so we can do a good job in comparing. The median values differ by only a factor of 1.75. If you compare the median value of the mass to flux ratio that we get in the simulation, it's comparable to the median value that Trollin and Crutcher got. Now, there are a number of differences, however, between our simulation and the observations. The first I've already emphasized, that is that our observations are for a single range of physical, a single set of conditions, whereas the observations average over many clouds There are very different kinds of clouds. Some of them are high mass star forming regions, some are low mass star forming regions. So it's just a complete hodgepodge. Secondly, the observations are smoothed over scale depending upon the resolution of the observations. The Zeeman observations were made with different telescopes that have different beam sizes. So, and furthermore, they looked at sources at different distances, whereas we just picked one size to average over. The maximum mass in our simulation is 74 solar masses, whereas for the OH observations it's 1,400, and for the CN it's 1,700 solar masses. Now, there are two factors, I think, that influence that difference. One is that in the observations, as I said, the best resolution that they had was a 0.03 parsecs that we used. But some of the telescopes have bigger beams and some of the sources are farther away. So obviously, as you average over larger volumes, you're going to get higher masses. The other effect is that our box size was limited to a little less than 5 parsecs. A lot of molecular cores that they saw are in much larger molecular clouds. And because of the line with size relation, that means that the Mach number that these cores are subject to is much higher than what the value of 10 that we used. And that could also have an effect. Then finally, the simulations were ideal MHD simulations. They do not include non-ideal effects like ambipolar diffusion, whereas, of course, Mother Nature has to include everything. So the inferences from the simulation are that contrary to the results of Crutcher, we do not find very weak fields. And as I've emphasized before, the RMS field divided by n to the alpha is larger than the median value of the line of sight field. Whereas they infer that you can have B total that might be as small as only 24% of it. Now I should say one of the things, their model is actually inconsistent, so there are two ways of calculating this quantity where I did the minimum value of B total. One is to actually use their B max, and that's what I did here. Another way to do it is to say, well, they have this square distribution, and then you can go ahead and, using that square distribution, get it. If you do that, you get the coefficient of 0.12, which is even smaller. So there is an uncertainty, but it's definitely smaller than what we find. Okay, now another fact, the thing that we found is we get an increase in the mass to flux ratio beyond the ideal MHD limit. So flux freezing implies that mu phi can decrease as matter fragments along a flux tube. So now let me go back to the picture we have where here's our turbulent box. We've got a magnetic field going in the z direction vertically here. And we calculated the mass to flux ratio. Initially, we said we took all the mass along the flux tube, along the whole 4.5 parsec tube, and we said, well, that's the mass in the flux, and that we got that, and we set that to 1.62. Now, if I go ahead and I say, well, all the mass in the top half of the room is going to gather into one cloud, and then all the mass in the bottom half will gather into another cloud, then each of those clouds will have the same flux, but only half the mass. So their mass to flux ratio will decrease. But what we find is an increase. We actually find that 55% of the cores have mass to flux ratios that are larger than this initial value of 1.62. The maximum value, in fact, that we find is 13, which is really huge compared, almost order of magnitude larger than the initial value. Okay, so that was summarize that. Let's go on to this protostellar accretion disk crisis that I mentioned. And as we'll see, this protostellar accretion disk crisis is going to be bring up something directly related to this increase in the mass to flux ratio. Okay, I'm not sure, Mark, how much do they know about class 0 sources?
They have heard about class 0 sources from Neil Evans. They also heard about disks in class 0 sources from Patrick Hannibal 2 weeks ago. So I assume they've forgotten.
Okay. Thank you, Mark. Okay, so observers divide protostellar sources into several classes based on their spectral energy distribution. And in fact, I think Stella showed some yesterday. Do you show some different, of the different classes? And They then correspond very approximately to different stages in the evolution. The class 0, as you might imagine, originally they had classes 1, 2, and 3, and so they had to stick 0 on it after observations advanced to the point that they could actually see them. So these are invisible in the infrared using 1990s technology. They also now are typically defined as having an envelope mass which is larger than the mass of the protostar. So this is then the earliest stage of protostellar evolution after you form the protostar. Eve yesterday talked about prestellar cores. That's before you even have the protostar formed. And the interesting thing is that class 0 protostars have accretion disks. So this is data from Jurgensen et al. In 2009. And here are a bunch of class 0 sources. And here are the envelope masses and the disk masses and the stellar masses. They don't know what the stellar masses are because it's not possible really to directly measure the mass of a protostar. So these all have disks, and these were made with, observed with a sub-millimeter array. And so these are disks have finite sizes. They're not just little teeny disks. Then more recently, there was evidence for a Keplerian rotation. And this, I think, is a very impressive piece of data analysis in which they used karma observations that had 1 arcsecond resolution. And that corresponds to 140 AU. And then because they built up the signal and noise, they were able to do what some people call sub-pixel imaging. So normally if you think about like your camera, you got so many pixels, you got 10 megapixels or something like that, and you think that the finest resolution you're going to get in your image is going to be determined by how big the pixel is. However, in fact, if you have very high signal and noise, you can infer information on scales smaller than the pixel. And here, because the signal noise is about 5, they can infer information down to about 30 AU. And here's the plot of they have the radius here and the velocity here. And then to guide your eye, they have this Keplerian rotation curve. And as you go to higher and higher velocity, and you're on smaller and smaller radii, and the data are consistent with this Keplerian rotation curve. So it's a class 2 source because the stellar mass, as inferred from this rotation curve, is about a couple of tenths of the solar mass, whereas the envelope mass is 1 solar mass. And they infer a disk mass of a little bit less than 1% of solar mass and a radius of about 90 AU. So this is definitely a significantly sized disk. Okay. Now we go back to the role of magnetic braking. If you remember when I was describing some of the classic papers, people pointed out that magnetic fields could essentially move the angular momentum, and that was good. That would allow stars to form. And in fact, then a little bit later, Mistel and one of, I think it was a student that he was working with, showed that this magnetic braking time divided by the free fall time, in fact, varies as this mass to flux ratio. So this makes sense. The magnetic braking time is going to get bigger and bigger as the magnetic field gets weaker and weaker. So when the field, remember the mass to flux ratio, the flux is in the denominator. So if the field gets weak, then mu phi gets big, and the magnetic braking time gets big also. So the simulations, however, led to a crisis. So I think the first example of this was in a paper by Tony Allen, Jian Li, and Frank Xu. And they were doing a 2D non-turbulent ideal MHD simulation. And they found that in order to get a disk, they needed to have a mass to flux ratio of more than 10. Whereas, as we've seen, the observations suggest that it's more like 2. Since then, Li went ahead and did more studies, and he went from 2D to 3D. He had added in all the non-ideal effects, including not only the ambipolar diffusion, but also Hall conductivity and resistivity. And he found that basically you could not get a disk. So there's a big problem here, which I assume Patrick told you about, which is, of course, you see disk. The fact that we are here means that there was a circumstellar disk certainly around the sun. And then I presented evidence to you that even at the class 0 stage, there are a circumstellar disk. So the one idea which Patrick came up with Chardy in 2009 is that if the disk were misaligned with the magnetic field, then it would be easier to form. And in fact, since then, just this year, in fact, Chad Hull and a large number of other people used Karma to observe the orientation of the magnetic field on a scale of 1,000 AU. And then they compared that with the direction of the protostellar outflow. And the protostellar outflow is determined on the scale of less than an AU. So you're essentially comparing things at 1,000 AU with 1 AU scales. And ideally, in all the cartoons you see in theoretical papers, these are perfectly aligned and everything is fine, except, as I said, you can't form the disk. If instead, what the observations show is that there is essentially random correlation between the orientation at the 1 AU scale and the 1,000 AU scale. So this, in fact, is expected in turbulent media. And what Hennebel and Chardy showed was that if this misalignment is actually 90 degrees, that's the biggest misalignment you can get, then you can get a rotating disk forming for mass to flux ratio bigger than 3. If it's 10 to 20 degree misalignment, you still do a lot better than the 10 that Allen et al. Found you get forming for 4 to 5. So what Mark showed in a paper this year is that if you allow for these weak fields to Crutcher, inferred, and this misalignment effect, assuming that it's random, then you conclude that 10 to 50% of the cores should produce a Keplerian disks. So another idea is that the disk just forms late. So the idea here is that the reason that magnetic braking works is that as the gas comes in and falls toward the star, it is essentially transmitting its angular momentum to the gas that's farther out. However, once all the gas has fallen in, there's no gas to transfer the angular momentum to, and so then it will conserve angular momentum, and you get a nice disk. So there are two problems with that, at least in my opinion. The first is that, as I indicated, it totally ignores all the gas that is outside the core that's forming. There is gas out there, and so that you can continue to transmit angular momentum. And secondly, as we've seen, class 0 protostars actually already have disks. This picture would suggest that they don't. So I don't think that one works. The third possible explanation is that the turbulence does it. So even though you have ideal MHD, they've done some simulations. First, Santos Lima and company made a toy model. I refer to that as a toy model because by the standards of people in this room, the simulation was kind of crummy. But nonetheless, it was good to demonstrate the principle. And they had a rotating gas around a half solar mass star, and they imposed Mach 4 turbulence on a scale of 1600 AU, which is much, much greater than is actually observed. But in contrast, they also did a non-turbulent case, and in contrast to the non-turbulent case, they found a perfectly good Keplerian disk, and they got considerable loss of magnetic flux in the inner regions. So Seefried and company have written a couple of papers, and they have found similar results. They considered the gravitational collapse of a 100 solar mass core. They put on a strong initial rotation in order to make it easier to form a disk. They had weak turbulence, and they start off with a mass to flux ratio less than 3. So they did a very high resolution AMR simulation with a resolution of 1.2 AU, and they found that they got Keplerian disks with radii between 30 and 100 AU. And this, in the more recent paper, they confirmed this basic result with a wide range of initial conditions. So basically, no simulation without turbulence, and that has the angular momentum aligned with the magnetic field, has produced an observable class 0 accretion disk. All well-resolved simulations with turbulence have produced such accretion disks. So then I just described in a little more detail the work that one of my students, Andrew Myers, did together with Andy Cunningham, Richard Klein, and Mark. And that was, we were looking at the formation of massive star, and we also, as a fringe benefit, got to study the formation of a disk. So our initial conditions are summarized here, and the key thing for this disk problem to note is that the mass to flux ratio was 2 for the core, but it wasn't completely uniform, so actually on the central flux tube it was bigger than 1. And it was slowly rotating, so we didn't have extra rotation as some of the other ones had. And we ran 2 cases, standard resolution of 10 AU and a high resolution. In the standard resolution, we didn't see the formation of a disk. So the level of turbulence posed is much greater than in previous ones, except for the Santos-Lima, and it's comparable to the level that you actually observe. And we did not allow the turbulence density to develop self-consistently. We just imposed the turbulent velocity field on the core, and we turned on gravity immediately. So we then found that we did get a Keplerian disk. So this is our high resolution run, and we ran to 2/10 of a free fall time. So here are a couple of density slices showing you what it looks like. So the scale here goes from plus or minus 500 AU, both on the X and Y axis here. We're looking down on the plane. This does not look like your normal disk. The magnetic field direction is sort of given in the by the white lines here. And then this is an edge-on view. This again does not look like your normal disk. But in fact, we're not saying that this is the disk. What we, I should, before going on to that, let me just point out that we did find that there was an outflow coming out along the axis. It had a velocity comparable to the Keplerian velocity, and that's consistent with observation. Because our resolution is much less than Mother Nature, our velocity, of course, was much less. And we found that a disk forms in the central region, so this little orange part here. So let me blow that up. So let me remind you, this is from plus or minus 500 AU. Here's a picture from plus or minus 50 AU, so we've zoomed in by an order of magnitude. And now you can see that there's a perfectly nice disk here, and these little arrows show the rotation. And the stellar mass is about 3.5 solar masses. The disk is about a solar mass, and the radius of the disk is about 30 AU at the time we stopped our calculation. Let me emphasize that we stopped the calculation fairly early, only after 6,000 years. And the central mass to flux ratio is increased from 5.6 to 20. But we got a beautiful Keplerian profile. So this in the straight line here shows you what you get for a 3.5 solar mass star, and you can see that the simulation works very well. But it's also true that misalignment of the angular momentum and the magnetic field could have contributed to the formation of this. Here's the misalignment, and so on small scales it's fairly well aligned, but on large scales it is very misaligned. So this large misalignment on the scale of 1,000 AU is consistent with the results that Hull et al. Found. So what accounts for the violations of flux freezing? So when I talked about the turbulent box simulation of a magnetized molecular cloud, I told you that in ideal MHD, fragmentation can reduce the mass to flux ratio, but it can never increase it. That's because you're just dividing up the mass on the flux tube, and the more I divide up the mass, the smaller the mass to flux ratio. But the simulated case, we actually found that this increased rather than decrease. Then we saw the formation of a Keplerian circumstellar disk from a turbulent magnetized core. There was a large increase in the mass to flux ratio in the central flux tube from 5.6 to 20. So there are 2 possibilities. One is that this is just numerical resistivity. Every code has numerical resistivity. Now we have verified convergence up to somewhat earlier time than the data I've been showing you, up to 0.37 free fall times. Running at higher resolution is extremely expensive, so we haven't really been able to go beyond that. The other possibility is turbulent reconnection, which leads to reconnection diffusion, and this has been basically an idea pushed by Alex Lazarian. So it's been recognized for a long time that reconnection could have a role in removing magnetic flux. Here's a cartoon I took from a classic paper by Peter Strittmatter, written in almost 50 years ago, showing that if you have a magnetic field which is threading this, that you can get a reconnection. So here you have an O-type neutral point. That little loop of field there can contract and disappear. An important thing to keep in mind about reconnection is it moves magnetic flux, but it doesn't actually destroy it. A lot of times in the literature, you will see statements to the effect that reconnection can destroy flux. It can't, but it does enable you to move it out. Another thing to note is that in this idealized picture here, all the reconnection is, in this case here, is occurring in this X point. That's a single point on this two-dimensional slice. If I went ahead and said, well, what happens in 3 dimensions? Well, that just then gives you a very thin ring. So you have all the reconnection is occurring in a ring. And because the volume of that ring is so small, it really limits the amount of reconnection that can occur. Now, in turbulent reconnection, though, you can get around that. So in a turbulent medium, the fluctuations in the magnetic field cascade down from large scales to small, and this was worked out in a theory by Goldreich and Sridhar. And then Lazarian and Vishniak showed that using this idea, you could essentially get a reconnection occurring throughout the volume of a turbulent medium. That changes things qualitatively. So Lazarian has then suggested that this volume pulling reconnection can lead to diffusion of the matter relative to the field. So in a way, you are now violating ideal MHD because you cannot get reconnection in ideal MHD. But what happens is because it's a turbulent cascade, you essentially start off with turbulence on a large scale, it cascades down to small scales, and when you get to small enough scale, then non-ideal effects come in. Now, precisely because the turbulent reconnection is based on this cascade, it's something that's naturally included in numerical simulations. So I said all we have is numerical resistivity, which is completely artificial, but that doesn't matter. As we improve our resolution, then our numerical resistivity will get smaller. Well, then what happens is that just means that the turbulence will cascade down to a smaller scale, and you'll still get the same reconnection. So in order to verify that this is in fact a physical effect as opposed to a numerical effect, then you just have to do a resolution study, and we're in the process of doing those now. So far, the data suggests that it is consistent with having the reconnection diffusion. So the effect of ambipolar diffusion on this turbulent reconnection is not clear, at least to me. We're now, as I said, we're undertaking numerical tests to confirm that our conclusions are independent of the numerical resistivity. And in the future, we plan on including ambipolar diffusion as well. So the key conclusion to take away from this is that it appears that ideal MHD is not ideal in a turbulent medium. In other words, the turbulent cascade will inevitably cause the process or fluctuations to cascade down to a scale small enough where non-ideal effects become important. So the conclusions then, we go back to the 2 classical problems in star formation that I mentioned. The magnetic flux problem, this is the one on the large scale that I mentioned where we just want to try to get the gas to become gravitationally unstable. So Mistel and Spitzer asked, how is it possible to get the mass to exceed this magnetic critical mass so that you can get the gravitational collapse? So observations since then have confirmed that Mistel and Spitzer were right. Atomic gas is magnetically subcritical. It is impossible for a gas to collapse and form stars in the atomic medium. On the other hand, observations have shown that the molecular cloud cores are supercritical. So GMCs are supercritical because they have column densities that are large enough so that they can overcome the magnetic field. If you remember back at the beginning, I said you had to have a flow over a scale of 500 parsecs in order to build up enough mass to become supercritical, and in fact GMCs are formed from gas on such a large scale. So while cloud cores can form by flows along field lines, it's really difficult for me at least to see if I'm having 100 parsec GMC, and so that will allow me to go ahead and allow the gas, if I contract all the way over the 100 parsecs, I can then form this one solar mass star that just doesn't make much sense that you have to gather gas from such huge distances to form a star. So this is then basically similar to the problem that Mistel and Spitzer pointed out. So our simulations show that the mass to flux in a turbulent medium increases more than expected in ideal MHD. So this is possibly due to reconnection diffusion. We've not confirmed that. And it may contribute to solving the magnetic flux problem. If this is true, then ambipolar diffusion may not be essential. So again, I want to emphasize that this is basically, we've been doing observation by computer, and so far the simulations are in very good agreement with magnetic fields observed along the line of sight. But we're able, of course, to study the full three-dimensional field. So then the second classical problem was the angular momentum problem. How can the gas lose 99% of its angular momentum in order to be able to form a star? And it was realized long ago and has been confirmed in many analytic and simulations that magnetic torques are very effective at solving this problem. In fact, they're so good that you wind up with the protostellar accretion disk problem, that you can really remove all the angular momentum, thereby preventing disks from forming. But there's a big problem, because we observe in these class 0, even in the class 0 stage, that disks have already formed. But again, just in terms of looking at the power of theory, this prediction was made long before protostellar accretion disks were even discovered. So then I cited several simulations that show that if you include turbulence, then you can get the formation of observable disks. And so this reconnection diffusion that Lazarian has been pushing is a plausible but as yet unproven explanation. I should say that Hennebel, I don't think, believes it. I think he focuses mostly on the misalignment. And I know that Seifried and their collaborators also don't believe it. So this still needs more work to be done, which we're in the process of doing, as I'm sure they are also. So ideal MHD is not ideal in a turbulent medium. Thank you. So I'd be glad to answer any questions if people have them.
All right, well, let's go to lunch.
Oh, wait, there is a question.
Sorry.
Simulations update the isothermal assumption. Do you think that that's a reason might heat up, or is that energy escape because they're transparent?
Yeah, so at the under the conditions we're looking at, the gas is transparent and the energy can escape. When you get, if you're actually doing a star formation simulation, you actually go down to much smaller scales than the 500 AU resolution we have, then you have to take that into account. But in this simulation, it's a pretty good approximation.